So we have seen a greedy algorithm for job scheduling with deadlines in which we selected jobs in decreasing order of price. Now we need to establish two results to justify this algorithm. The first is to do with the criterion for checking if a set of jobs is feasible as a schedule. And the second is to actually demonstrate that our greedy strategy is optimal. So let's get to the first result. So we had the following theorem. We said that let J be a set of jobs, say 1 to K, then J is feasible. In other words, all the jobs in J can be scheduled to meet their deadlines if and only if J can be scheduled in order of deadlines. So in other words, supposing we assume that these are actually ordered by deadline. So the deadline of 1 is before the deadline of 2 and so on, which is, and deadline of K is the last job, and then we schedule in the sequence 1 to K. So in other words, if this is the property that the deadlines are in this sequence, then we should be able to schedule it in that sequence, and if we can't schedule it in that sequence, then this set is not feasible. This is what we claimed. So now let's establish that this theorem is actually true. Okay. So suppose J is feasible. Okay. So let, as before, we assume that J is given actually in the order that the greedy strategy would have used, in deadline order. Okay. So we are currently maintaining J in this order, but J is feasible, but perhaps not in this order. So suppose R1, R2 to Rk is a feasible schedule. So this is not the schedule that we have assumed. So what we will show is that in fact this schedule can be modified to the schedule that we had above. Right? So now let's look at our schedule. So our schedule is 1, 2 up to K, and the schedule that we are given, which is feasible but not the same, is R1, R2 up to some Rk. So it is some permutation of 1 to K. So there is some earliest position, let us call it A, okay, where these two disagree. So A and RA are not the same. Now A of course is in this order 1, 2, so the previous one is A minus 1, next one is A plus 1 and so on. So up to this point, so R1 is 1, R2 is 2 and so on. So up to A minus 1, these two sequences are the same. So this means that if RA is not equal to A, it must be something bigger than A, right? So this means that A is less than RA. In other words, RA comes from somewhere here, and therefore A is less than RA. And then because of our assumption, this means that the deadline of the job A is less than or equal to the deadline of the job R of A. Okay. Now let's look at this schedule again. So A doesn't appear here, but A must appear in this permutation somewhere. So A appears somewhere later on at some position B. Okay. So now from this we know that the deadline of A is actually equal to the deadline of R of B, because R of B is exactly the same job as A. From these two facts we can conclude that the deadline of R of A is greater than the deadline of R of B, right? Because deadline of R of A is greater than A, and A itself has the same deadline as B because it's the same job. Now since the deadline of R of A is greater than R of B, okay, and R of B is, it is possible to schedule R of B here, so R of B is still within its deadline, and A has a deadline even further to the right, it's possible to exchange these two, right? So it's possible to exchange these two. So what we now have is that we have 1, 2 up to A, okay, and then up to K as our original schedule, and the new schedule we have now swapped things, so we have R of B and R of A exchange up to R of K. But the point is that now at this point, okay, we have got A is equal to R of B. So therefore now our schedule agrees at one more position. Okay. So now we can go to the next position where the two schedules differ and do the same argument to agree that we can modify the blue schedule to look one more step like the green schedule. So eventually the given schedule is transformed to the one that we had, 1 to k, right? So in other words, we start with an arbitrary schedule and then each discrepancy we fix by observing that we can swap the discrepancy position with something further to the right and retain feasibility, and therefore by repeatedly doing this we transform any given schedule to the ones 1 to k, and therefore 1 to k must be a feasible schedule. So it is sufficient to check if 1 to k is feasible, and this is particularly easy to do because we just have to check that at each position I, the deadline is bigger than the position, right? So that's why it's important and it's very helpful for us. So we have seen that our feasibility check is in fact correct. So now we are left with the task of showing that the greedy algorithm is actually optimal. So to recall, the greedy algorithm picks jobs in descending order of profit, and it selects each job provided it is feasible with respect to the currently selected set. And it keeps going, and our claim is that the set of jobs you collect in this fashion overall has the maximum amount of profit possible. So suppose we have another solution. So let's first start by labeling. So the greedy solution, let us say, so let us call the set of jobs that we collect by the greedy solution I. And then we have, suppose we have a different solution which is optimal. Let us call that J, right? So now the question is that if I is equal to J, then of course greedy is optimal. So the interesting case is when I is not equal to J. Right? So if I is not equal to J, we have to somehow argue that I is still optimal. Now the first observation we make is that if I is not equal to J, then I and J are incomparable. What we mean by this is not the case that either of them is properly included in the other. So we want to rule out, for example, that J is properly included in I. So this is not possible because then J is not optimal. Right? If J is properly included in I, however we pick J, turns out that there is an extra job in I which is compatible and can be added to J, so we can increase the value of J, so J is not optimal. So it cannot be the case that J is properly included in I. For the same, by a similar argument, we can argue that I is not properly included in J. Okay, because any missing job, any job which is in J but not in I, is compatible. So any missing job is compatible with I, right? Because all of J is feasible. So if we add the job which is missing in J to I, it would be feasible. So when we enumerated the jobs, at that particular point also it would have been feasible. So we would have added it to I. So therefore, we can conclude that I and J are incomparable. So what this really means mathematically is that some A belongs to I but not J. So there is a job A which belongs to I but not J, and there is a job B which belongs to J but not I. Right? So there is something in I which is not in J, there is something in J which is not in I. So now the first thing we will do is we will look at the highest profit job in I but not in J. So let us give this a name. So let us call this job A. So A belongs to I, A does not belong to J, and among such things it is of the highest profit. Now let's look at any B which is from the other way. It belongs to J but it doesn't belong to I. So there is no constraint on B. It is some job which exists in J, does not exist in I. Now the claim is that the profit of A is at least as much as the profit of B. And the reason for this is the following. If suppose we have the other way around, that B which is in J has a strictly better profit than A. Now let's assume that we arrange J also in descending order. descending order of profit. Remember that I is already selected in descending order of profit, so let's arrange j in the same way. Right? So now we come down, so we have I here listed out in descending order of profit, and we have j listed out, and then at some point we hit a job B which is in j, and we have a job A which is in I. And now if this is better than that, then B would actually have been considered for selection earlier. Right? So I would have encountered B before A in the greedy strategy, and then B would have been included. Right? So if this is the case, B would have been included in I. Because B is compatible with everything here, so it would have been considered somewhere before A, so it would have been compatible with everything here, and therefore it would have been included. So PB cannot be greater than PA, so the highest profit job in I where it is not in J is definitely at least as profitable as anything which is in J but not in I. So we'll keep this in the back of our mind, and we'll proceed to the next step. So the next step is to look at the schedules SI and Sj. So this is the actual sequence in which I and J are supposed to be executed in the two solutions. Okay? So what we want to do is we want to make Si and Sj agree on the time slots for all common jobs. See, right now there could be a job which is in I and also in J, but it could be executed at some time t in I and at different time t prime in J, and we don't want that to happen. Right? So we have these two schedules, Si and Sj, right? And now we look for a job which is in I and in J, but which are at different times. And we won't do this in an arbitrary way. We'll start from the right. So we'll come backwards, and we'll find the first position in either of them where this happens. So for instance, it could be that I have a job X here, and the same job in the second schedule is not here but earlier, because I'm starting from the right. Okay, so I didn't find it here, I found it later, going from the right, so it's earlier in time. This is one possibility. And the symmetric possibility is that when I started from here, I found a job, say Z over here, and it happened a little earlier in I. Right? So among these, if I were going, because Z happens before X, I would pick Z first. If Z was to the left, I would have picked X first. So basically, I'm starting to the right, and either I or J, I find the first discrepancy. So let's look at the green case to begin with. The purple case will be symmetric. Right? So here is the green case. So I have some job X here, and the same job X appears in the other one, but earlier. So what I do is, I look at this corresponding point in Sj. In general, there will be another job here, Y. Okay? So now Y is feasible at this point, so Y is also feasible at any earlier point, because it meets its deadline here, so it can happen earlier. It may not happen later, but it can happen earlier. So it is possible for me to move Y to the position of X. At the same time, since X is known to meet its deadline over here, I can move X to the position of Y. So therefore I can rearrange Sj so that X happens at the same time as Si and Y moves early. Okay? And in the symmetric case, you would do exactly the same thing, but you would do it on the other side. So if I had the picture where I had a Z here and I had Z in I at a different time, then again I would look at this particular slot and see that there is a Y here, and I would say that this Y can move here and this Z can move here. Now of course there is no guarantee that there is a Y here. There may be no job scheduled at a given slot, because we don't really claim that the optimal schedule has consecutive jobs. But if there is no job, it's even easier. I just have to move X. I don't even have to swap. So similarly, I just have to move Z. Right? So what we have done here is that we have fixed one discrepancy between Si and Sj. Right? So we have fixed one position where they two had the same job, but they were at different times. So having fixed this, I can repeat this. So I repeat and fix another one. So I can keep doing this until I get, so sometimes I change J, sometimes I change I, it depends on what happens. So in general, I would have changed both and I would have gone from Si, eventually I would have gone to some S prime I, and from Sj to some S prime j, and the property that I have is that these two things now agree on common jobs. So every job that is in both I and j is executed at exactly the same time in S prime I and in S prime j. So now we have a situation where we have established the following two facts. The first fact is that if A is the highest profit job such that A belongs to I and A does not belong to J, right? The highest profit job in I but not in J. Then we have PA is bigger than or equal to PB for any B that is in J but not in I. Right? This is the first thing that we established. The second thing that we have established is that now S prime I and S prime J agree on the time slots of all jobs in the intersection. Every common job has the same time. Okay? So now given these two facts, we will now try to convert the solution J to the solution I without sacrificing optimality, and in this way establish that I is also optimal. Okay? So what we do is we now look for that job A that we have identified earlier, the same job, the biggest one here. So we look for this job A in S prime I. Right? So if I look at S prime I, okay, then there is some job, there is some position where the job A occurs. Now, because this is not a common job, okay, the corresponding position here has some other job. Let us call it C. Okay. Now this C cannot be also in I, because if it was in both I and J, we have already ensured they appear at the same time, so it would appear in the top as well. So C must be in J, but C is not in I. There is also a possibility there's nothing here. We will deal with that later. But right now, let's assume that we have C in J, but C not in I. And we know that A is in I, and A is not in J, and it is the highest such priority, and therefore it satisfies things. So therefore, in particular, we have that P of A is bigger than or equal to P of C. So what we can do is we can replace C by A in J. So I can knock off this particular job, and I can say I want A here instead. Now this is compatible because A is feasible at this point, so it's feasible at the same point. And now what have I done? I've replaced C by something which is at least as big as C. Right? So the value of J, okay, is not affected. It cannot go down because J was optimal. A is at least as big as C. It cannot go up either because A is optimal. So actually the value must be unaffected. It must be actually equal. So in other words, we actually should have that P of A is equal to PC. Okay? Now in case there was no slot here, then in fact we would increase the value of J, and this is not possible. So actually there must always be a corresponding job on the other side such that A and C can be exchanged. Right? So what we have done now is that earlier we had I was not equal to J, and now we have reduced the difference by one job. Okay. Now I again look for, so J has now become some J1. Okay. So now I look for A which belongs to I or A prime such that A prime does not belong to J1 of highest profit. Now with the same logic, we will find that P of A prime is bigger than or equal to P of B for any B which is in J1 but B is not in I. Okay? So we'll have the same argument as before, and therefore this new A prime again can be replaced. Okay? So again we replace A prime into J, and so we keep going, and eventually we will transform J to be the same as I. Okay, and each step preserves optimality. Therefore, since each step preserves optimality, eventually J is optimal, so I has the same value as J, so therefore I itself was optimal. So this is similar to arguments we have seen before. You take any optimal solution and step by step you transform it to be equal to the solution that greedy produces, and hence the greedy solution itself is optimal. Okay, so to summarize, we have established two things. The first is the feasibility criterion. So we said that any set J can be executed if and only if J can be executed in deadline order. So this means that we don't have to look at all possible reorderings of J to determine feasibility. It's enough to sort it in ascending order of deadlines and check that. And the second thing is optimality. So we have shown that the greedy solution is in fact optimal. Right? And this we showed by saying that any other optimal solution can be transformed step by step to a greedy solution without sacrificing the value.